Welcome back to the deep dive. We're exploring the OEIS again, the online encyclopedia of integer sequences. Today, it's A000360, distribution of non-empty triangles inside a fractal rep4 tile. Quite a mouthful.
It really is. It signals this fascinating blend of geometry and pure numbers.
Right. So our goal today is to sort of unpack that for you, the listener. Bridge that gap between, fractals and sequences. It sounds complex.
It has layers, certainly, but the core ideas, I think, are quite elegant. We want to show how these intricate shapes connect back to, well, number theory.
Okay, let's start with the geometry then. Break down these terms. What's a rep4 tile?
Sure. So a reptile is basically a shape that you can cut up into smaller, identical copies of itself.
Like a square, you can cut it into 4 smaller squares.
Exactly. That's a perfect example of a rep4 tile, specifically tiled by 4 copies. Now, add fractal to that.
Okay. That's where it gets complicated.
Well, it means the shape has that self-tiling property, but often its boundary is infinitely complex. Think fractal coastlines, that kind of self-similarity at all scales.
Yeah.
Or shapes built recursively, like those based on L systems.
Got it. And non-empty triangle. Sounds simple, but I guess this distinction matters here.
It's crucial. Non-empty just means a triangle with a positive area, a real triangle.
Not just points on a line that happen to connect.
Precisely. We're excluding degenerate triangles. The side lengths have to obey the triangle inequality.
Yeah.
Any 2 sides added together must be longer than the third side. Like a 3, 4, 5 triangle works.
But 2, 3, 5 wouldn't count.
Right, that just makes a line segment, 0 area.
Yeah.
A000360 only tallies the proper area having triangles.
Okay, so we have fractal rep4 tiles, and we're counting real triangles inside them. What specific object are we looking at for A00000360?
The sequence is tied to a very specific, rather intricate object called the Gosper-Lafitte triangle.
The Gosper-Lafitte triangle.
Okay. Yes. And Azer's 000360 counts these congruent, non-empty triangles, specifically along lines sort of perpendicular to the base of this fractal structure.
So it's like taking slices through the fractal and counting?
Essentially, yes. It's mapping the distribution of the density of these triangles across the structure.
And that gives us the sequence. 1, 0, 1, 1, 1, 1, 2, 0, 2. Wow, it jumps around immediately.
It does. That variation, especially the zeros, tells you something.
What do the zeros mean? Are there just gaps?
Exactly. It means at that specific location or cross-section within the Gosper-Lafitte triangle, you either hit an empty region, or maybe the only triangular configurations possible are degenerate ones. 0 area.
So the geometry is clearly complex, but you said this links back to number theory, right? This is where it gets really interesting for me.
It is quite remarkable, yes. How does this seemingly chaotic geometric count connect to, well, fundamental arithmetic?
So what's the connection? How does this pattern map to known sequences?
Well, add 000360 has this surprising link to a really classical sequence, the Stern-Brocot sequence, which is A002487 in the OEIS.
The Stern-Brocot sequence. That's fundamental in number theory, isn't it? Related to rational numbers.
Deeply related. It can be used to generate all positive rational numbers. And researchers found that you can derive A000360 directly from Stern-Brocot.
How?
You take the Stern-Brocot sequence, apply a modulo 3 operation to its terms, and then just drop the very first term. What's left is A00000360.
That's quite something. So the way these triangles are distributed inside this complex fractal shape is directly governed by a sequence that organizes rational numbers.
It points to a deep underlying order, doesn't it? It's not just random distribution.
It really does. Is there more structure, like a recurrence relation?
Yes, there is. It adds another layer of proof that this isn't chaos. For instance, the even terms of A000360 follow a very simple rule, A to n plus AN1.
So the count at an even position depends additively on counts at earlier positions, n and n1.
Exactly. A simple recursive structure emerges from this complex geometric counting process.
So let's wrap this up. What's the big takeaway for you, the listener? A000360 is showing us hidden order.
Precisely. It's a map of structure within a self-similar shape. It shows that the geometry, the counting, the number theory, they're interconnected in profound ways.
The visual complexity gives way to arithmetic predictability.
Yes. And maybe a final thought to leave you with. The fact that the physical arrangement of actual non-degenerate triangles inside a fractal follows rules derived from something like the Stern-Brocot sequence. Makes you wonder, doesn't it?
Wonder what?
What other kinds of patterns, what other seemingly chaotic distributions within fractals or other complex systems might also be governed by surprisingly simple arithmetic rules? Perhaps rules we just haven't found the right perspective or the right numerical mapping to see yet.